Suppose we have a function f which is one-to-one and differentiable and has an inverse function f inverse. I want us to consider f inverse prime of a. So this would be the derivative of the inverse function. Let's note that a is a y value for f, because here we're putting a into something related to the inverse. By the definition of derivative, f inverse prime of a is equal to the limit as x approaches a of f inverse of x minus f inverse of a divided by x minus a. Now let's see what we can do with these expressions here. If we let f inverse of a be represented b and f inverse of x be represented y, then f of b is equal to a and f of y is equal to x. Since by assumption f is differentiable, f is continuous. If f is continuous, we've already seen that f prime would then be continuous. And by definition of continuity, that would mean that the limit as x approaches a of f inverse of x is equal to f inverse of a. Using the expressions that we've already considered here, we can rewrite this limit as the limit as x approaches a of y is equal to b. In other words, as x approaches a, y approaches b. So continuing on with matching these colors, f inverse of a and f inverse of x here, and then I'm going to add a couple of other colors for x being f of y and for a being f of b. So we're going to use these expressions down here, or these equations down here, to replace the expressions in this limit. So f inverse prime of a is equal to the limit as y approaches b, because we have that as x approaches a, y approaches b, of y minus b over f of y minus f of b. Here are the colors. So what we had originally written as the limit as x approaches a of f inverse of x minus f inverse of a divided by x minus a then gets replaced by the limit as y approaches b of y minus b over f of y minus f of b. Now I'm going to do something that may be a little bit weird. We're going to consider 1 divided by the reciprocal of that. So 1 over the limit as y approaches b of f of y minus f of b divided by y minus b. And so I've made it the reciprocal, but then I've used the reciprocal of the original fraction that we had. But take a look at what we have in the denominator. In the denominator, we have f prime of b. So this is the reciprocal of f prime of b. If we consider now that f prime of b has b as its argument, and the fact that b is f inverse of a, we can then rewrite this as 1 over f prime of f inverse of a simply by replacing b with what we had already said, f inverse of a. So to summarize or recap, if f is differentiable and 1-to-1, then f inverse prime of a is equal to 1 over f prime of f inverse of a. So we've got a derivative of an inverse, and it turns out to be the reciprocal of the derivative of the inverse evaluated at a. And this generalizes if we replace a by x, and then instead of a number, we would have a function. Let's see why this reciprocal should make sense. Here we have the graph of a function, which I'll call f inverse, and associated with that function, well, we'll just put a point on it, and we'll say that that point has a y value of a. Now, associated with that point is a tangent line, and that tangent line has a slope, commonly referred to as rise over run, but formally we're going to say it's delta y over delta x. Now, as you may recall, there's a reflection property here. and the graph of the inverse of a function is a reflection about the line y equals x. So in this case, the inverse is f. And on f, there's an associated point that has an input of f inverse of a. That should make sense. A is a y value, and so the inverse of f evaluated at a should be an x value. Now associated with that point is a tangent line, and since x's and y's have all been interchanged, the rise over run has a different relationship, right? What was vertical for f inverse is now horizontal for f, and what was horizontal for f inverse is vertical for f. In other words, the slope is the reciprocal. To describe this reciprocal in words, the derivative of the inverse of a function at a value is the reciprocal of the derivative evaluated at the inverse value. I'd like to close out this video with an alternative approach for the formula we developed here. We're going to use implicit differentiation. If we have that y is equal to f inverse of x, then it would follow that f of y is equal to x. So f prime of y dy dx would equal 1 by taking the derivative on both sides with respect to x. And you remember, I'm sure, that if your inside function is not x and you're differentiating with respect to x, you end up with a derivative of the inside function. Really, this is the chain rule. Solving for dy dx, we get that dy dx is then equal to 1 over f prime of y. And doing the same kind of substitution that we saw a few minutes ago, y can be replaced by f inverse of x. So dy dx then becomes 1 over f prime of f inverse of x. Now you might ask, well, if we could have done it this way, why did we do it the other way? But think about it, if I had started with this one and then tried to show you the other one, I don't think it'd go over very well. This way you appreciate this one more.